Hello, everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker on chapter 11. So this is our environment, and we're going to work through an example that allows us to do a linear regression. So what I'm going to start with is this first line that says my file gets file.choose. So the less than and minus sign is an assignment, and I'm going to state it as gets whenever I mention it in the videos. What this file.choose function does is it opens up a window so that if you have a data set saved on your computer, it will give you the entire path of that data set. So I'm going to triple click on that. And in our studio environment, you can press Control Enter if you're on a PC. If you're on a Mac, you're going to use Apple Enter, or if you're uncomfortable with keyboard shortcuts, you could always press this Run button, and that will run the highlighted section. I'm going to use the keyboard shortcut and press Control Enter, and I see that a window pops up, and I'm going to be able to navigate through my computer to find out where my data set is saved. So I have it saved as chapter 11, part 1 example data set, and this is CSV file. I'm going to double click on that. And then if I were to just run the line that says my file, it tells me the entire path on my computer where it's saved. So I could have wrote this out on my own, but for now, I just figured it might be easier since everyone's path on their computer might be different where you save the data set. But essentially on my computer, it's saved in the C drive under users, hammer, desktop, stat350b, chapter 11, part 1, example dataset.csv. That would be a lot to type out. But from now on, whenever I call that file, it's going to use this path exactly. So I have it right here under this next function that says read.csv. So what read.csv does is it says, hey, I have a data set saved called my file. Can you open that up and save it as a data set called data? So I'm going to run that line of code. And you notice that now I could look at the full data set if I wanted to. There's 11 observations, X and Y, and it tells you all the X values and all the Y values in that data set. All right, I could get a summary of that data set. And when I do that, it will tell me the 5-number summary plus the mean. So the average for X is 2.882 and the average for Y is 2.355. Okay, I'm also getting the 5-number summary, the min, the first quartile or the 25th percentile, the median, the 50th percentile, the third quartile, the 75th percentile, and the maximum value. Okay. So what I could do here so that I don't have to keep pulling off the data $X as the X values is I'm going to just assign X to be data $X and Y to be data $Y. At this point, even though I see this X and Y, if I entered X, it should give me an error because it's not found. And if I enter Y, it should also give me an error. However, if I do data $X, there's all the X values that you expected as part of this data frame. And if I do data $Y, I should get all the Y values. Now, I don't want to use the $sign to have to keep on picking off the X and Ys because I just want to simplify my code for a minute. So I'm actually going to assign X to be data $X and Y to be data $Y. And once I do that, if I put in X or Y, they should show up as vectors. There's the X vector and here's the Y vector. Now, something to note is that R is line by line programming. So what happens is that it will read exactly what you've read in, but it does not go back and change anything in the past. So you just need to be aware that when you run something, it matters what got ran before it. Okay, N is my sample size, and I'm going to just use this function called length to say, what's the length of X? And it wouldn't have really mattered if I did the length of Y, because really both X and Y have 11 data points. Another note is that wherever I have this pound sign or hashtag sign, those are comments in my code. So it doesn't matter what I write after the pound signs, they won't be ran in R. R will ignore them. All right, so a few things that were asked for is if we use our X squared values. That is literally just squaring every value of X. So if I have X is 2, then X squared is 4. If I have X is 2.25, X squared is 5.0625. I could do X times Y, right? Which 2 times 1.60, that's going to give me a value of 3.2. Similarly, I could calculate Y squared, which would be all of my Y values squared. So 1.60 squared is 2.56. Let's just double check. R is like a giant calculator, so I could do 1.60 squared, or similarly, I could do 1.60 times 1.60. And no matter what, I'm going to get 2.56. But essentially, R is way faster than I could ever be because it could do all those squared values for me at once, whereas I would have to do them individually by hand. That seems like a lot of effort for something that isn't really serving me well. Okay, so there was a table in our lecture notes that said calculate X, Y, X squared, X times Y, and Y squared. And if we did that, you could get this entire table in one fell swoop. Okay, and I could turn that into a data frame by using the as.dataframe code. And from there, that allows me to be able to pick off any value I want. So I could do $X now, $Y, okay? And if I do that, that should still just give me the X values and Y values that I had before. All right, I am going to do a shortcut where I could use the apply function. Now, apply is very special because it will take any data frame, which I called T, and if I put a 1 in here, it'll do the rows, but if I put in a 2, it'll get the values for the columns. So what I want to do is I want to sum up every column in T. So I'm going to use the apply function. I'm going to do T2 for columns and then sum. And I'm going to just call this summary. From there, I'm going to get the names of my summary. And remember, if you think about what makes up T, then we know that we have our sum of our xi's, our sum of our yi's, our sum of our xi squareds, our sum of xi times yi, and the sum of the yi squareds. So these are the values of all of those summations. All right. We can calculate x bar in the regular way, add up all the x's, divide by n. Y bars, add up all the y's, divide by n. All right. We're not going to be printed the x bar and y bar until we put them by ourselves. So if I just wanted to print x bar on its own, I could do x bar. If I just wanted to print y bar on its own, I could do y bar. But if I wanted to just push them together, I can use cbind, which means bind these together by columns. And I get the values of 2.88 and 2.35. Now, notice that my summary also had that sum.xi. Let's just double check that our sum of x, 31.7, was equal to the very first value. Oh, there it is, 31.7. Okay, so in our notes, we had the equations for the sum of the x deviations squared, the sum of the y deviations squared, the sum of the x deviations times the y deviations. You can double check these formulas with the lecture notes or with your textbook. And we can print those out. So verify that you can get these same answers. And then if you remember, we also had equations for beta hat 1 and beta hat 0. Okay, so we can get our predictions for the slope and the y-intercept by using the formulas. Okay, so our y-intercept is 0.256 and our slope is 0.7279. Now, this seems like a lot of work for a very simple thing that we could probably do a very, very big shortcut to. And in fact, we can. All right, if I wanted to, I could use a function called LM, and that stands for linear model. And I can say, let fit.lm, this is a name I made up, get the linear regression model where I regress y on x. So from that summary, voila, in one line of code, I get those same exact beta hat 0 values and beta hat 1 values. So remember, before we calculated beta hat 0 was 0.2568, and here it is again, 0.2568. And then the beta hat 1, 0.7279. And once again, I get the same exact value, 0.7279. So in one line of code, we did all of the equations that we talked about within the lecture notes. And from there, I can actually just plot my x and y values, which I should have probably done before we did anything else, right? And when we see this plot in general, there's a positive slope, right? And we can mess around with the plot to make it look prettier if we wanted to, or we could just put in the fitted regression line right away. All right, so these are our xi, yi hat values, right? So this is our prediction line. So notice our points don't lie directly on the line, but this line is the best fitting line to minimize the sum of the squared errors. Okay. How do we calculate those actual squared errors? Well, first we could think about our residuals. We have our observed values minus our fitted values. Observed minus predicted. That will give us our residuals. Or similarly, we could have just picked them up by doing fit.lm $ residuals. And we should get the same exact values. So you can see that there's always multiple ways to do things in R. Some ways are easier than others. Some require you to know what you're able to pick off. But one way I could have known what was available to me is I could have said names of fit.lm. And right there, it'll tell me, hey, by the way, you could pick off the coefficients. That sounds like something useful. You could pick off the residuals. You could pick off the fitted values. So if I do fit.lm $ coefficients, and I check that out, that's just going to give me the y-intercept and the slope. Pretty fantastic. All right. Remember, we talked about the sum of squared errors. If we want to know what our actual sum of squared errors equal, well, in this case, it's 1.2896. So you could have done all of this by hand. And if you would like to do this on a TI-83 calculator, I'm sure you can. If that's your preference, do that. If you're using some other programming language, go for it. But this just gives you an example of how you can work with the data and start programming in R. I know it might seem like a lot, but as we go through in the semester, it's going to get easier and easier. I hope that you learned something in this video, and I'll see you next time.